Yeah, thanks everyone for joining Sameela today. So today we have Sameela presenting, who recently submitted her PhD thesis. So very exciting. And she's going to talk about basically one half of her thesis today. And yeah, it's a project that I'm quite excited about. It's a project where we will invest a bit more from Optima and from the team here at Monash to actually now implement the stuff that Sameela is presenting today. So yeah, hope you get some interesting ideas from this and some feedback. And if we can get some feedback afterwards, that will also be super useful for us. Right, I think good to go, right?
Yeah, thank you so much. So yes, as you get introduced, I'm Sameela, and yeah, okay.
And just use the keyboard.
Yeah. Hey, good afternoon to all of you, and I'm Sameela, and I'm thankful to this opportunity given to me to share my PhD thesis with you. So the overall idea of my thesis is to bring down the barrier between the domain experts and constraint optimization technologies. In doing so, I propose a shift from the traditional approach of modeling for domain experts to modeling with them. So in this talk, I'm going to present the first contribution of my thesis, which is a visual specification technique that we call Constraint Entity Relationship Diagrams, CERDs for short. And before I dive down into the Constraint Entity Relationship Diagrams, let me first set the background so that we are using the same terminology throughout the talks. So as you are aware, the constraint optimization problems are when you have to find a combination of choices that satisfies a set of constraints and optimizes an objective. Simply, when you're creating a roster or even when you're packing your grocery bags, you're solving an optimization problem. A modern approach to solve these problems is through using problem-specific models along with generic solvers. Now, in the first phase of this process, a modeling expert would formalize a problem of a domain expert into a mathematically precise description that we call a model using a high-level modeling language such as Minisync, Essence, or even Python. And then in the second phase, models are instantiated with data. So the model, along with its data, we call it a problem instance. And then in the third phase, the problem instances are automatically solved using pre-built solvers such as Gurobi and Simplex to produce solutions. Now, a model created at the end of a model development stage actually can produce high-quality solutions. But then, unfortunately, their adoption in real-world systems remain lower than we expected. So, if our models can produce high-quality solutions, why aren't they being adopted in real-world use as we expected? In my thesis, I identify four interconnected challenges that particularly happens during the model development phase that lowers this adoption of our models. First one, as you all know, creating a model requires a specialized skill set. And that means either the domain experts actually have to learn a modeling language or hire a modeling expert who can do a model for them. And in practice, the latter is more common. Secondly, at the moment, the domain experts are only indirectly involved in the modeling process, where they might give informal feedback or provide us with data and documentation. And together, these two challenges actually lead to the third challenge, which is the limited understanding of optimization models by the domain experts. That means more often, the domain experts actually see the optimization models as black boxes. And this reduces the trust, the confidence, and also the transparency of our models. And also, the limited involvement of domain experts in the early stages can lead to a fourth challenge, which is the limited understanding of optimization problems by the modeling experts. And that means there's a risk that the modeling experts will start to formalize a model without a sufficient understanding of the optimization problem that they're solving, which can lead to incorrect models and costly rework and solutions that fail to meet the domain experts' needs. So, what are the current approaches that the optimization community has attempted to improve adoption? Firstly, we have tried to reduce the expertise required to build our models by introducing universal modeling language such as Minisync, and also more recently by introducing visual modeling tools such as Solvay. Now, in both of these approaches, the target is to delegate the modeling responsibilities to the domain experts. But even with these technologies, building an efficient model actually requires substantial expertise. The second approach to improve adoption is by integrating the domain experts into the model plus solve process. This is typically done through interactive user interfaces where they provide interactive optimization systems that provide interactive user interfaces to allow the users to add preferences to guide the solving phase. For example, in a multi-objective optimization problem, user interface can be used to display an initial solution, allow the end users to fix some parts of the solution, and then define a secondary optimization criteria and re-optimize. Of course, the interactive user interfaces can help understand the end users how the system responds to different inputs, but they do not necessarily change the black box perception of the model that's being used to solve these problems. So we had a look at how the software engineering addresses a similar set of challenges. Now, sustaining domain experts' engagement during the early stages is a widely recognized challenge in software engineering, mainly sourcing from the limited understanding of software systems. And rather than trying to reduce the barrier of entry for the end users to master a programming language, the software engineering clearly recognizes and distinguishes the roles like end user, the business analyst, and software engineer. And then it gives a range of tools and techniques to improve the collaboration, shared understanding, and communication during the requirements engineering phase, which is the first phase of software engineering. So of these techniques, we were particularly interested about graphical system models. Now, the graphical system models, they don't give a complete representation of a software system. They are rather abstractions and partial views of the system. And there are many types of graphical software systems that's being in use, but we were we identified the structural models as the most useful or most suitable to reduce the black box perception. Now, the structural models captures the system components and the relationships. The most popular structural model that's in use is the UML class diagrams, which captures the problem in terms of classes and its associations. Entity relationship diagrams used in database design also can be, it matches the definition of a structural model, but then they are more often referred to as data models. And when it comes to optimization models, both of these diagramming techniques can capture an optimization model up to some extent, but neither is sufficient to express the full complexity of an optimization model. And when it comes to optimization modeling languages, such as SCOMA and Minisync very recently, supports object-oriented style modeling. So in such cases, the UML class diagrams would be a better fit to represent such models. But then majority of the optimization modeling languages actually doesn't support the object-oriented style modeling. So in that sense, the ERDs is a better fit to represent the data components of an optimization model. So let's have a look at like how far we can go with representing an optimization problem using an ERD. So to do that, I'm first going to introduce you to a hypothetical knapsack variant problem. So the idea is to produce an optimal purchase and a packing plan. Now, suppose there are some shop owners with a limited budget who wants to bulk purchase items that belongs to a certain item type from a wholesale market. And the overall idea is to maximize the resale profit and minimize the number of boxes used to pack these purchased items. And the boxes used can be single colored or multicolored. And then they have a box type like plastic, cardboard, and thermal. And then box types are associated with the capacity, and item types are associated with volume, purchase price, sales price, availability, and profit. And when creating the purchase and packing plan, we have to respect the constraints like you can't purchase more than the budget, you cannot purchase item types more than the availability, you can't pack items more than the capacity of the box type. And then, if possible, no more than 3 items must be packed in blue boxes. And there are also some packing constraints like no hot and cold food together, no detergent and food items can be packed together. And before we actually try to map this problem into an ERD, let's look at the problem through the lens of an optimization model. So in an optimization model, we have, the parameters, which is like the input data. So now, okay, sorry. Yeah, so we have parameters, which is like the input data. And so in our example problem, the budget, the boxes and the color, the box type and the capacity, item type, the volume and purchase price, etc. are going to be the input data or like the parameters to the model. And also when expressing the constraints 5 and 6, we have to capture the hot and cold status of the item type, detergent and food status of the item type. And then we have the variables. So the variables are the major decisions that must be made to solve a problem. So in our problem, we have like how many of each item types is packed in which box is going to be the variable. And then we have the objective function, which measures the quality of the solution. So in our example problem, maximizing the resale profit and minimizing the number of boxes used to pack the purchased items is the objective function. And then we have the constraints, which are the restrictions imposed on the parameters and the decision variables. So when it comes to constraints, we have 2 major types of constraints. The constraints that must be satisfied, so we refer to them as hard constraints, and the constraints, the soft constraints, which are like desirable to be satisfied, but it's okay to violate them as well. So let's now see how each of these components of an optimization model is actually mapped, can be mapped into an ERD representation. And when it comes to ERD notation, there are lots of variations in ERD notations, and I'm presenting the ones that we've chosen to extend to this the new visual specification technique. So in ERDs, the entities represent things, aspects, objects, or events that can exist independently. So in our problem, the boxes, the box type and the item type are the entities of the problem. And these entities corresponds to set of occurrences of the same real world concept. For example, for box type, the occurrences are the plastic, cardboard, and thermal. And then the relationships define the association between those entities. In our problem, we have a packed relationship between item types and boxes, and then the boxes has box type relationship. ERDs also provide notation to represent certain types of constraints, especially related to the relationships. The cardinality constraints tells you how many of one item type is linked to how many of the other entity. And then participation constraints tell you if all occurrences of an entity must participate in a relationship or not. Now, again, in ERD notation, there are multiple ways that you can represent cardinality and participation constraints, and we have chosen the Crowswood notation to do that. And let me explain that to you with an example. So what this notation means is that for one occurrence of a box, there must be exactly one box type. And for one occurrence of box type, it can be assigned to 0, 1 or more boxes. And then in an ERD representation, an attribute is a characteristic or a property of an entity or a relationship. So in our problem, the boxes has the color, box types has the capacity, item types has the volume, purchase price as the properties. So, and also the hot and the hot, cold, detergent and food statuses of each item type. And so this can be like indicated as attributes of the item type entity. And then when it comes to the relationship between item type and boxes, how many items of each item type is packed into a box is actually an attribute of the packed relationship. And then there are special types of attributes in ERDs. So the primary key attributes uniquely identify the occurrences of an entity. And then the multi-valued attributes can store more than one value. For example, the boxes can be single-colored or multicolored. So that's a multi-valued attribute. And then derived attributes can be derived from existing data. For example, the profit is the difference between the purchase and the sales price. As you can see that ERDs can capture some components of an optimization model, but then it is also missing some important details like the objectives and the other constraints. So we extended the ERDs with new notation to accommodate these missing details. And the extended version, we call it Constraint Entity Relationship Diagrams, CERDs for short. And so let me now explain how I extended the ERDs to the CERDs. Recall that in ERDs, we cannot differentiate between the input data and the output data. So, but in an optimization model, it is very important for us to differentiate between the parameters and the variables. So we used color coding to differentiate those two. And then again, ERDs can capture some constraints like the data type and domain related constraint and cardinality and participation constraints. But then when it comes to optimization models, we have more complex and different types of constraints. So we introduced two types of constraints into the CERDs. The first one is the functional constraints. So they are used to define how derived attributes and derived variables are being calculated or how they are being derived. So we denote the functional constraints using a rounded rectangle shape, and all the functional constraints are also having a unique label starting with FC. So FC1 state, the profit is the difference between the sales price and the purchase price. And FC3 here says how the box profit is being calculated. And we use natural language to specify the constraints, but with a set of recommendations. So we recommend when you're writing the natural language specifications, use the entities, attributes, and relationships that's already there in the diagram and use bold highlighting. And then we also introduce a new link type called constraint participation links to connect the constraints to the related attributes and relationships of the functional constraint. And any other constraints that cannot be categorized into data type, domain, cardinality, participation, and functional constraints are categorized as general constraints. The way to express general constraints is like pretty much similar to the functional constraints. The only difference is that it now has a label to state whether it's a hard constraint or a soft constraint. And if it is a soft constraint, a weight associated with it, like a weight that defines the relative importance of the soft constraints. And when it comes to this weight, it doesn't have to be reflected in the optimization models, but it is just an indicative value for the domain experts and the modeling experts to come to a mutual understanding about the relative importance of the soft constraints. And then it also had a unique label starting with GC for the general constraints. There are some other recommendations to write natural language specifications, which I'm not going to go into detail, but I'm happy to share my thesis with you if you are interested to know more about it. And the objectives, to represent objective, we introduced a new tape shape symbol. And then to represent each objective components, we introduced, we used derived variable attributes. For example, in our objective component, we had, in our objective, we had two components. One is to maximize the reserve profit and to minimize the total capacity of the boxes or number of boxes used to pack. So as you can see, the label, there's a unique label defining the optimization direction, which is like whether each objective component should be maximized or minimized, and then also followed by a weight stating the relative importance of each objective component. In this case, the reserve profit is more important. Maximizing reserve profit is more important than minimizing the total capacity of boxes used to pack. And then we use the functional constraints to define how each objective component is being derived. All right, so that, of course, with the complexity, as you can imagine, when the complexity of the diagram increases, the complexity of the diagram increases with the size of the problem and the number of constraints. And that actually reduces the readability and the comprehensibility of the diagrams. To tackle this challenge, we have introduced layering. Now, layering helps to group the similar components together in different canvases so that you can represent the data type related constraints in one canvas, functional constraints in another, and general constraints in another. And then use progressive disclosure, like I did during the presentation, to reveal the details step by step. So that the user get to see only the level of details that's needed at that point of time. All right, so now we've had a look at the the third notation. So let's look back. What are the design goals of SERDs? Firstly, we wanted to provide support clarity and simplicity by providing an intuitive visual notation. And then we wanted to ensure expressivity by providing enough visual constructs to adequately specify an optimization problem. And we wanted to ensure traceability by providing clear guidelines to map between the optimization problem, SERD, and the optimization model. And then we wanted to ensure, encourage shared understanding, knowledge transfer, and communication during the model development phase. And by shared understanding, we are actually referring to two complementary perspectives. That is the problem understanding of the modeling experts and the model understanding of the domain experts. The third design goal of the SERD is to provide early validation so that you can have a common reference point that evolves with the model. The fifth design goal is to provide precise and complete problem specification by minimizing under-specification, over-specification, and incorrect specification of the problem. And to see whether the SERDs have actually met these design goals, we conducted user studies. The other goals of the user studies was to identify the limitations in the notation and also to identify suitable features for a dedicated SERD authoring tool. Because at the moment, we are actually creating SERDs manually using a very general diagramming tool called Draw.io. So the user studies were carried out using two types of workshops. In the first workshop, the modeling expert created a SERD for their own case study after a short introduction and a practice session. And in the second workshop, the modeling experts used the SERDs that they created in the first workshop to communicate with the domain experts, again, after a short introduction session. Workshop ones were carried out in individual sessions and also sometimes in shared sessions. 7 real-world case studies participated in the first workshop with 8 modeling experts. And but in the second workshop, only 4 out of the 7 case studies participated. And the workshops were conducted like 1 each per case study. So in total, there were 4 modeling experts and 4 domain experts. And both workshops were concluded with questionnaires to capture the experience gained, to assess the experience that they gained through the workshops, during the workshops. Now, these 2 workshops actually produced a lot of data. So because we had observational notes and SERD artifacts created during the workshops, we had the audio and video recordings and 3 types of questionnaire responses. And we used mixed method analysis with the help of MaxQDA tool to produce the results. And again, we had a lot of results. I won't be able to go into detail of all of that, but I'll share some of the important ones with you. So when it comes to clarity, all the all the participants, both the domain experts and modeling experts, agreed that the SERDs are clear and effective in representing an optimization problem, and the visualization actually improves the understanding and the communication. But when it comes to simplicity, we received mixed views. Particularly during the workshop 1, we could see that the modeling experts experienced a steep learning curve. And we think this is partly because we had only 15 minutes introductory session, and the session would have benefited with a longer introduction with few different types of examples. However, in workshop 2, even after a short introductory session, the domain experts actively engaged in discussions. So what happened is, during the workshop 1, because there was a limited time frame, the modeling experts simplified the problems represented in the SERDs. So in the workshop 2, the domain expert actually identified those simplified places, and they tried to expand the SERD diagram during the session, which is really good. And then when it comes to expressivity, the workshop 1 identified some components that are difficult to express using SERD notations, and we worked post-workshop to improve the notations. And the notation that I introduced to you is the improved version. And we also use this improved version during the second workshops. And again, natural language specifications received mixed views, where like the modeling experts bought into notice the trade-off between the precision and the accessibility. Whereas like there was a clear preference for natural language from the domain experts to express the constraints. Having said that, there was one domain expert who had a mathematical background. He preferred like a formal notation to represent the constraints, mainly for the brevity and also for precision. Which also means that the preference for natural language is actually dependent on the background of the domain expert. And user studies also identified many strengths of SERDs, which actually aligned with many of our design goals. So modeling experts appreciated the SERDs as a guide for communication. So the modeling experts who were at an early stage of the modeling process used the visualization to explain, this is what we think your problem is. And the modeling experts who were with a more mature model, so towards the end of the project, used the SERDs to explain, this is how your problem is mapped to the model. And interestingly, there were also 2 domain experts who had joined the project only halfway through, and they appreciated the SERDs for its ability to be used in the onboarding process, where it can be used to explain, this is the problem that we are solving. And we also could notice the modeling experts used layering and progressive disclosure during the workshop 2, particularly for the big projects. And for some small projects with small modeling components, actually prefer to have the entire diagram because it avoids the premature disturbance or premature questions appearing in the halfway through the narration. And then they use labeling to guide the discussion. That means they followed the numbers in the label so that it's it makes a story. And then sometimes when the domain experts wanted to specifically refer to a constraint, again, they use the labels to refer to certain parts of SERD and discuss further. Interestingly, they also used concrete examples when explaining things. For example, in the SERDs, we use item types, which is an abstract representation. But when explaining, they would use like ice cream or milk rather than using like item type. And then some domain experts also, so some modeling experts also use sketches to establish the terminology first before starting the explanations with the SERDs, and like use the same terminology during the explanations. As for the black box perception, surely the SERDs reduce the black box perception. So even the domain experts who had a clear understanding of the optimization model mentioned to us that the SERDs definitely make it clearer, like the model clearer to them, because the visualization makes the abstract components and their relationships very visible. And also it was appreciated by the domain experts who didn't have a mathematical and a technical background, because the SERDs use natural language to explain the constraints. As I mentioned to you earlier, during the second workshop, the domain experts identified many missing details and like the simplified places in the SERD, which means that SERDs has the potential to reduce under-specification, over-specification, and incorrect specifications. And we also try to, like in the SERD notation itself, we also try to make make the often underspecified detailed explicitly specified. For example, we have notations to capture the attribute types and the domains, cardinality and participation constraints, optimization direction, and the relative importance, which is often missed in the first discussions. And then the soft and hard status of the constraint, again, we often miss that in the initial discussions. And then the relative importance of the soft constraints. And finally, when asked about the strength on sets, both the modeling experts and domain experts mentioned that it's a good, it provides an approach to agree with each other, and that would reduce the misunderstanding and refactoring needs in the future. The main limitation that we identified in sets is its disconnection from the underlying model. We purposefully designed the sets to be implementation independent. That is, one set can be implemented using many viewpoints. But having said that, this is advantageous as well because it abstracts and hides the complexity of the model. And on the other hand, the disconnection actually comes from the natural language specifications, because now you can't automatically compile that to automatically compile the constraints to a model. And the second limitation is the design cost and the maintenance. And there were a few modeling experts who mentioned that there's a chance that they would use the surds in the initial phases, but they would eventually give it up and then do the refinements directly to the model. And then, I'm sorry. And then there were a few projects with heavy data pre-processing steps. As to run the model, they had to perform a lot of data pre-processing steps to prepare the data for the model. So those modeling experts mentioned that surds felt incomplete without these data pre-processing steps. But that also shows the need for such visual representations that can work alongside surds. And as future works, I'm very excited and very happy that we've secured the grant to create a dedicated set authoring tool. And in my thesis, I also present an approach, a generic approach to convert a surd into a minisync model. I'm excited to try that in the new tooling as well. And most of all, our field is growing and our optimization problems are becoming bigger and bigger. And I think there's a need, we would benefit from adopting some engineering practices in the model development process. And I believe there's so much space to grow in that research direction. All right, thank you very much. And I'm taking a moment to especially thank Guido and Maria for helping us to helping me do this work. Yes.
Any questions?
I have a question for slide 56.
Yeah.
There was a slide that you mentioned that you had to add few constraints, maybe 55 or 56. So there was a slide you said for additional changes, you need to add the general constraints and hard future importance, soft constraints, and those kind of things as a future work or something, right?
Sorry, can you repeat it?
So you had you said that you might need to extend it, that there were some, you need to do data pre-processing and you need to add the generalized of constraints and those kind of things.
Yeah.
So my question is, so then how do you think that a domain expert would take these? Because these are, again, comes to a technical perspective. So how would you think a domain expertise would tackle these things? Because then these are technical terms for them, right? So so how would you think a cert would be if you implement them in a cert that a domain expertise would be able to grasp them?
You're saying extending the certs to capture the data pre-processing?
No. So you said that you're going to add more general constraints, soft constraints, then the importance of the objectives and those kind of things.
Yeah.
So that would become the a cert.
They're in there. Yeah.
They're already there.
So then it makes a bit more complex. So my question is, how would the domain expertise would tackle them when we have those things like? So still they are a bit of technical terms. So let's say a simple domain expertise, how would you think that they would tackle the cert?
Like during the workshops, the introduction that we gave was just 10 minutes to 15 minutes. But even with that, they could understand the concepts. And I think the domain experts quite understand like the soft and hard. They might not know the word, but when we say like there are constraints that must be satisfied and there are some, if possible, type constraints, they surely understand that. And the notation, I think, is clear enough for them. Yeah.
David? On Zoom, David?
Yeah. Hi, can you all hear me?
Yes.
Yes.
Yeah. Yeah, great talk. Age-old question, how we communicate our stuff and how we get people to actually use it and maintain it as well, for that matter. So I guess a couple of things. One, where would you publish this? So I mean, you're doing a thesis, so perhaps I know the Journal of Applied Analytics, the old Interfaces journal, is interested in this sort of stuff typically. And now I've forgotten the second part of my question, but perhaps where are you looking to publish this as far as journals go?
Yes, that's a good question. We are actually planning to publish in the visualization journals. Like, I think it's I can't remember the name of it, but like it's a visualization related journal. I'm just starting to write up the like I'm actually considering to write up there. And I also considered the ACM journals for human-computer interactions because of the user study component. Yeah, so it's either the visualization journals or like the HCI side of
Okay.
things.
All right. Well, good luck with that. The second part of my question is, I guess, the responses you get. I mean, it's hard. How do you sort of separate the subjectivity of it? So, I mean, some people learn differently. People pick up things differently. I'm a visual person, so having visualizations appeal, but others are more audio, oral. Others are more kinetic. So it's quite possible that the responses people give to you might be influenced by the way they pick up things. So you probably need a pretty big sample size for that. Have you sort of factored those things into your efforts at all? Just quantifying the effectiveness of what you've done is, I guess, is going to be a challenge. Is the underlying question.
Yes, that's true, and I believe if we can get the if we can get the tooling done, then we can do another sort of user studies using the tool and perhaps the undergraduate students, so that we have more participants in the workshops. So that's one consideration as well at the moment.
Okay, cool. Well, good luck. This could be a seminal bit of work that you're doing. If you sort of, provide some insights for people to use, that'd be really good. So yeah, good luck.
And about the current workshops, the good thing about it is that we did it with real domain experts and the real modeling experts. So I think the feedback specifically from the domain experts is like worthwhile to assess and improve the notation. And then of course we can evaluate the tool later on.
Cool. Okay. Thank you.
No?
Yes, I think I have a two-part question. With the authoring tool, is there the idea that you could maintain the two representations of the problem, so the graphical and the mathematical, so that if someone came along and edited the mathematical one, it would directly update the graphical and maybe vice versa?
For the tooling, yes, we are considering that, and to connect it to particularly to Minisync.
Yeah.
And because Minisync also supports object-oriented concepts now, and it's easy to map the entities to the object classes.
Because I think that would be quite useful in making sure that the graphical model was up to date with the mathematical one, because you mentioned that as the model gets developed, people start to refine the mathematical version and maybe leave the other one. The second part is I thought that tool could be very useful for teaching people about optimization, having the graphical and the mathematical and showing how, okay, if I change this mathematically, this is how it changes in the graphical. Yeah, that was
I think just having, so let's say you change a constraint in the model and it uses different variables. So the CAD is clearly out of date. Just being told, okay, well, whatever you've done here, with either what you're doing here is wrong, or you have to update the CRD. That just even that level of checking would be very useful, because I do think the real benefit comes from this having it last for the entire life of the model.
Yes.
Yeah.
Yeah, I think especially together with the layering idea, right? So you can have one document that captures everything from the actual model that is executable all the way to a high-level document that is much, much more abstract, but it's all kind of kept together and kept synchronized. I think that's what we're aiming for.
Yeah.
I look forward to playing with this tool.
And I personally believe that it would be beneficial in the teaching, Minisync courses as well.
Yeah.
Well, not just, maybe you can, separate from Minisync just for a moment, but just optimization modeling in general.
Yeah.
Yeah, I guess once you've done it from Minisync, then, okay, how different to change it to Ample, for example? Something quite different. Might be tricky. Maybe AIMS is better. It's more object-oriented. Right?
I was thinking not even just the mathematical, as in
just the mathematical description.
The graphical, and just understanding how to write optimization problems.
I mean, you obviously have to instantiate the decision variables, like how they actually represented, right? That's one of the choices that happens. And then you have to instantiate the constraints. And that's tricky.
There aren't that many different options.
No, and that's true.
So it's,
But I'm interested in because one of the things I hope you'll be able to find out of this is you'll say, okay, now I'm trying to specify this constraint and I cannot do it. Essentially, I need to build another view of the data in order to write that constraint. And that forces me to go back to the entry relation to CERD and actually add in some new functionally defined structures because that actually more accurately represents what I actually have to do. Because I can write in English something that's perfectly good, but which has no implementation without some extra stuff.
Yeah.
Any other questions? Any more from Zoom? Or from here?
I have a third part to that question that I asked, because one thing I was thinking about, particularly because you've got the natural language representation of the constraints with guidelines about what everything means. I thought, okay, well, an LLM or something could be used to help with, I was thinking, could an LLM be used to then take that representation and instantiate the mathematical model?
Definitely can.
Yeah. Yes. And I think from a natural language specification to a model, it's difficult, but from a third to a model, it's definitely it could be a very accurate model, in that way.
And we know that the other direction also works, right? So we've just run, Jason just ran tons of Minisync models through LLMs to generate README files for them. And they understand them quite well. So they can they can generate natural language representations of individual constraints as well. So you could, like, if you're halfway through a project and then use a tool like this to suddenly kind of explain what you've done, that could also be useful. Yeah. All right. Final chance to ask a question. Otherwise, thanks, Sameela, again.